So that's a chemical formula. It's a molecular formula, so it gives us the actual exact number and type. Now, this is where we get into cutie pie and best friend. Cutie pie and best friend. All right, so protons and electrons. Show me with your hands. Are they attracted or repulsed? Proton and an electron are attracted to one another. They have opposite charges. A proton and a proton. An electron and an electron. Okay. This is constant dance. So, I'm going to weave you a story about cutie pie. Cutie pie, the object of your affections. That individual who you just have the most desperate crush on. You're so attracted to cutie pie. Cutie pie is just everything that one could ever want in a partner. You really wish cutie pie would go to the dance with you. Okay? Ah, cutie pie. Unfortunately, cutie pie has got the most obnoxious, horrible, repellent, awful best friend in the world. And cutie pie and best friend are never far from one another. So as much as you're attracted to cutie pie, every time you get close to cutie pie, there's best friend. I hate best friend. Cutie pie is so wonderful. Best friend is so awful. So, this is the dance that happens in covalent bonding, okay? Cutie pie! Best friend. Because the protons in one of those atoms are tremendously attracted to the electrons in that other atom. Cutie pie! However, the protons in that one atom are also repelled by the protons in the other atom. Best friend. And the electrons in that first atom are repelled by the electrons in that second atom. Other best friend. Yeah, exactly. So there's this dance that goes on between the attraction of the nucleus of your first element for the electrons of your second, and vice versa. I mean, that attraction is mutual. Cutie pie loves you as much as you love cutie pie. Sadly, you might have an obnoxious best friend too. However, those nuclei repel one another. And those electron clouds repel one another. So what these atoms will do is there's this sort of dance, this balance. You get as close to cutie pie as you can, while keeping best friend at a distance that you can tolerate. Okay? So when you get to that perfect balance, that's the distance where those atoms are going to sit, essentially, in their bond. That's how far apart they're going to stay. They're going to balance the attraction for cutie pie with the repulsion of best friend. Okay? I always think of Seinfeld and Newman when I say that. I guess I didn't get that to you.
I like Seinfeld.
Okay, good. So,
I actually watched Seinfeld.
they're going to get to that distance, and at that point, they're stable. At that point, they're no longer racing towards one another based on the attraction of one nucleus for the other's electrons, nor are they flying apart based on the repulsion of their electron clouds and their nucleuses. Does that make sense? So it's just this kind of dance to figure out where they're going to form a bond. Okay. The distance between those two atomic nuclei is the bond length. Now, we talked about a distance between atomic nuclei before. And what were we talking about in that case? Atomic radii. And in atomic radii, we were specifically talking about the distance between, half of the distance between two identical atoms that were bonded together. Here we're talking about any atoms. And we're talking about the whole distance, not half of it. And that's the bond length. So, bond energy is the difference in the potential energy when those two atoms are rushing towards one another because of their attraction. They're not stable. when they're flying apart because of the repulsion, they're not stable. When they get to that balance point, they're very stable. They have very low potential energy. If we go back to thinking about our boulder on a hill, they're sitting at the bottom of that hill. They've got very low potential energy when they're balanced. And they've balanced that attraction and repulsion. So the bond energy is that amount of difference. It's how much energy it would take to break that bond, or how much energy is given off when they form that bond. Okay? And there's a little graphic here. That same graphic appears in a slightly different form in your book. If we look at, I'll use my big hunk of metal to point this out. If we look at this graphic, here we have two atoms that are repelling one another. Their nucleuses are repelling one another. So you're being repelled by best friend. That's high energy. It's unstable. If they get down to this point where where the attraction and the repulsion are balanced, and they're very, very stable, they're very low energy, they give off that much energy when they form that bond. If they move a little bit further apart and they're being attracted again, the protons on one being attracted to the electrons on the other, they're racing towards one another again, then they're again not stable, and they're back up to this higher energy condition. Okay? Make sense? We'll do lots more questions.
For bond energy, it's how much energy it takes to break the bond, and how much it takes to...
It's how much energy is given off when the bond forms, and it's how much energy is absorbed, or how much energy it takes to break that bond. Okay. This little chart of bond lengths, I'll expect you to have memorized by tomorrow. You'll have a quiz on it. Joke. I just like to do that and watch your little faces go. Okay, so what you can see here, and there's a similar chart in your book, is that bond lengths vary tremendously. There's a lot of difference in how long these bonds are. We go from a hydrogen-hydrogen bond of 74. I think the units would be picometers. That can't be right.
It says PM there.
Oh, okay, it would be picometers. Yeah, okay, it is picometers. 74 picometers all the way up to a really long bond, bromine-bromine, 228 picometers. Iodine-iodine, 267 picometers. So what I want you to look at is hydrogen, hydrogen, and iodine, iodine. Look at the bond length, look at the energy. Jot down any notes you have about what trends you see. I'm going to